Okay, so the next one is 62. Now here we have three groups G, H and K, and among these H and K are subgroups of G and K itself is a subgroup of H. That means K is a subgroup of H and H is a subgroup of G, such that the index of H in G is M and the index of K in H is N, which simply means that there are M distinct left cosets of H in G and N distinct left cosets of K in H. Now obviously K is a subgroup of G, so we have to show that the index of K in G is Mn, M times N. So that many left cosets of K in G are there that we have to show. Also we cannot assume that G is finite because G may very well be infinite. So let's see the solution. So in the beginning itself we are going to list all the distinct left cosets of H in G and all the distinct left cosets of K in H. Let the distinct left cosets of H in G be G1H, G2H, etc. because there are m number of them, GM, H, where you of course understand that these GI are coming from G because these are left cosets of H in G, and the distinct left cosets of K in H similarly be H1K, H2K, etc. because there should be n number of them, so HNK, where the HJs are coming from capital H. Okay. Now consider the following left cosets of K in G, which are these. Let me write like this: GI H J K, where I varies from 1 through m and J varies from 1 through n. Now we are going to make two claims. The first claim is that this list of left cosets of K in G actually takes into account every left coset of K in G. That means you consider any left coset of K in G, it's going to be one of them. And the other claim is that they are all distinct in the sense that in total there are mn cosets listed here. So that would prove our claim, the thing that we want to prove in this exercise. we first claim that the above list contains any left coset of K in G. Now we need to prove this first claim. So let's take an arbitrary left coset of K in G. Let Gk be any left coset of K in G. Okay, and we just simply means that this element G is coming from G. Since G belongs to G and G is the union of all the left cosets of H in G. That is, G is this union. G, how many were there? M. We have G belonging to GIH for some I in this range, and this of course is, this fact that G is the union of all the left cosets, it's a part of the total claim that the left cosets of any subgroup of a group forms a partition of the group. So their union is going to be the whole group. So because G belongs to G, so G must belong to at least one coset in this union. So let that coset be GIH. Then G belonging to GIH means what? Then G is equal to GIH for some element H in H. Okay, but just like the left cosets of H in G form a partition of G, the left cosets of K in H also form a partition of H because K is the subgroup of H. But H is equal to H1K union H2K etc. union H and K. So this H will belong to one of them. So H belongs to HJK for some J in this range. Thus, K, this is not K, this is H. H is equal to HJK for some K belonging to K. Hence, okay, now if H is HJK, so we can replace H here with HJK. Hence, G is equal to GI HJK. This K is the element K, and that's why this belongs to GI HJK. Okay, so now you recall that this was our arbitrarily chosen left coset of K in G. Now this left coset obviously contains the element G itself, because G appears in this left coset as G times identity GE. G is equal to GE. So this left coset of K in G contains G, but G also belongs to this left coset of K in G. Now because K is also like H a subgroup of G, so the left cosets of K in G will form a partition of G, just like these cosets form a partition of the G. The left cosets of K will also form a partition of G. So that is why, due to this partition property, two left cosets are either disjoint or identical. These two left cosets are not disjoint because both of them contain G, and that is why they have to be identical. Since G belongs to GK and also G belongs to GI HJK, we have, in fact it need not even be mentioned that that's why they are equal. That comes from the partition property, that GK is equal to GI HJK. So our first claim has been established, which was what? It's that in these cosets, in this list of cosets itself, we have taken into account all the left cosets. This proves the first claim, or this proves our claim. Okay, now we are going to make the next claim. Next, we claim that the list that is our list GI HJK, where I varies from 1 through m and j varies from 1 through n, has mn left cosets. For this, we are going to prove like this. We are going to prove this second claim like this. Let I prime j prime be integers such that I and I prime lie between 1 and m, j and j prime lie between 1 and n, and these two left cosets are identical, which are, of course you can guess, one of them is GIHJK and the other one is GI prime HJ prime K. If in spite of having these two things distinct, say distinct integers, or these two integers distinct, if we still have this equality, then of course in our list of cosets there will be collapse. I mean, there will be repetitions in the list, and then the total number cannot be mn, it will be less than mn. But we have to show that that cannot happen. So we have assumed that for such a set of integers, the corresponding cosets are the same. Now we need to prove that Gi is equal to Gi prime and Hj is equal to Hj prime. That's what we have to prove. Okay. Then what do we get from this? Note that this element that is giving this left coset on the left hand side of this equation, that is GIHJ, itself of course belongs to this coset, because you can consider GIHJ times E the identity element. So let me instead of writing then, let me write like this: since GIHJ, which is GIHJE identity, belongs to GIHJK, and that is of course equal to this. So GIHJ being in this coset on the right side will be of this form: Gi prime Hj prime K prime for some K prime belonging to K. Okay. Thus, now we need to manipulate this equation a little bit. So this equation of course can also be rearranged. I mean, the terms can be rearranged like this. Should I do it in steps, or I can do it at once also? You will understand. So what I am going to do now is that I will pre-multiply both sides by the inverse of Gi prime. That is, I am going to do this. Now if I do this, what happens to this Hj? I am coming to that later, but we have pre-multiplied by Gi prime inverse. So on this side, this Gi prime will vanish and we will be left with Hj prime K prime. Also simultaneously we are post multiplying both sides by the inverse of Hj. So that is why the Hj has vanished here, and that is compensated by Hj inverse on this side. And this right hand side element actually belongs to what? It actually belongs to H. Why does it belong to H? We of course understand that this Hj prime and Hj and hence its inverse, they belong to H, because this Hj prime, Hj, these are elements that are coming from our subgroup capital H. However, what about K prime? K prime belongs to K, but keep in mind that K itself is a subgroup of H. So after all, K prime is also in H. So that's why this element itself belongs to H. In brackets we can write this. Note that K is a subgroup of H. So we recall this, and because of this the right hand side, hence Gi prime inverse Gi belongs to H, and this gives rise to the next equality. This implies that GIH is equal to Gi prime H. How this element belonging to this subgroup H implies that these two left cosets are equal, this part I am leaving to you. It's not very difficult. You just have to prove that, that means this is given to you. You have to prove that those two left cosets are equal, which you can prove by proving this first, that the left side is a subset of the right side. Let me just show you briefly. So to prove that this containment is true, you take an arbitrary element from here, say GIH, okay, and you have to prove that this GIH is equal to GI prime times something coming from capital H. So because we want Gi prime, so we just make it appear and then compensate for that like this, Gi H. Okay. Now you see why this thing is useful. Gi prime inverse Gi, which is what we have here precisely, this already belongs to H. So you multiply that by H. So that means this part belongs to H. So that is why this element belongs to Gi prime H. So that just tells us that this is a subset of this. Similarly, you can prove that this is also a subset of this by using this in a slightly different way. Instead of using that this element is in H, you may need that fact that its inverse also belongs to H. So that is why those two things are equal. Okay. But now let me keep it like this, not including it in the actual solution. But now what can we say from this equality? Recall that these were our distinct left cosets of H in G. Distinct. Okay, what that means is that if these suffix values are different, then the left cosets must be different, or more simply, if any two such Gi and Gj are different, which of course happens when the suffixes are different, then the cosets are different, because this is precisely the list of all distinct left cosets of H in G. Now here we have got two such left cosets where the representative elements are coming from this list, that means some Gi prime. But since they are identical, so Gi and Gi prime cannot be different. They have to be precisely the same thing. And that is why, so we continue our solution from here. Should I write the distinctness? But you understand, let me just simply write. But this implies that Gi is equal to Gi prime. Now we can use that fact in this equation. So you can cancel Gi and Gi prime from both sides by using the left cancellation law that you have in your group. So now the implication is this. So, or rather let me write like this. From this, we have, so if we cancel this same thing, they are the same from both sides, then we get this. Hj is equal to Hj prime k prime, or Hj prime inverse Hj is equal to k prime, which belongs to k, so just like this belonging to H implies that these two left cosets are equal. Same thing, all exactly same structure. You see, in place of I, now we have J prime, here we had I prime, there in place of H we have G. That's it. So just like that, this also implies, now we can get rid of this. This implies that Hjk is equal to Hj prime k, but then again that same or similar argument, because just like these are all the distinct left cosets of H in G, the distinct left cosets of k in H were these. H n k. So two such cosets being identical simply implies that the representative elements Hj and Hj prime must also be the same element. Hence, Hj is equal to Hj prime. So we have ended up proving precisely what we wanted to prove, that Gi is equal to Gi prime and Hj is equal to Hj prime. So in that list of all left cosets of k in G, actually all the Mn symbols listed are in fact all distinct left cosets. This, or we can write like this also. Thus, the second claim has also been established. That means there are mn left cosets. Let's write it in words. That is, there are mn left cosets of k in G. In other words, the degree of k in G is mn. And note that in this solution we have in fact nowhere used any finiteness of the group G, or in fact the subgroups K and H also. Nowhere have we used any such assumption that any of these three groups is finite. They may very well be infinite. For example, so here the solution ends. You can consider your group of integers under addition. This is an infinite group. In this, you have the subgroup of all even integers under addition. This is also an infinite group, an infinite subgroup, but the index of this subgroup in the group of integers is 2. It is finite. So in such cases also the result is true. So with this, the current set of exercises is over. The next chapter is factor groups and homomorphisms, which we will start in the next Lee update. And tomorrow, of course, we have our usual real analysis. So that's just it for tonight, and wishing you a very happy new year also. So see you tomorrow with real analysis. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.